All right, so here's the problem we hadn't quite finished up yesterday. We had this function y equals 3x to the 2/3 minus x squared. What did we do with this? Well, we found the domain was, what's that? Finish that one? Which is the one that, was there a different one we started on?
Yeah.
Quantity x squared minus 1 times.
It was a fraction.
Oh, do I have the wrong, what the heck? What's going
Started
on?
on Friday and then finished today, or yesterday.
I wonder if I didn't save, oh, I didn't save it, darn it. Oh, well, okay. Okay, you guys keep me up to, or you guys get me up to speed with this. Now, give me what the function was. Grace, what was the function? Okay, hey, quiet, please. What is it?
Hang on. So it's x cubed divided by x squared minus 1.
Oh, that's right, that's right. We were doing the slant asymptote. Okay, and so we had figured out, we said that the domain was not equal to, x not equal to plus or minus 1, right? We took, we divided it out. We went through that process of dividing it out, remember? And we said that this is equal to, if we divide it out, we just got x plus, what was it? What would it be? Somebody have written down?
It was x plus.
So something x over,
X squared minus 1.
X.
what was the numerator of that?
X.
X, okay.
What was there?
Okay. So that was, if we divide this polynomial out, this is what we get, right? And then we said in the limit that x goes, or that x goes to plus or minus infinity. Remember what happened? We said that this rational function would go to 0, and so it just looks like the limit of x, right? And so it's we get this asymptotic behavior. It's not horizontal, it's not vertical. It looks like the line, we get a slant asymptote. Whoops. Slant asymptote y equals x, right? And so that tells us, a little bit more than just when x approaches infinity, the function goes to infinity. It tells us that it does it along this line, right? So that was kind of slick. And then what else did we say? We took a derivative, as I recall, and you can just tell me what that answer was. How about?
X to the 4 minus 3x squared divided by the quantity x squared minus 1 quantity squared.
Okay. And we were finding the critical numbers of that. I think that's where we left off. Is that right? Okay. And so we said, remember we said that we get critical numbers where the derivative is undefined or equal to 0, and it's undefined at plus and minus 1, but it's not in the domain anyway. So those aren't critical numbers. Those are vertical asymptotes, right? But it is equal to 0 when the numerator equals 0. And so we were just solving that equation. And I do believe that's right about where we left off.
Yeah,
Right?
you just told us that we can't move it over and divide out the.
Right, good. Yeah, we can't, there's a temptation sometimes to just scoot this term over there and divide away the x to the 4th, which I understand why that would be a natural thing to do, because we oftentimes do stuff just like that. If you're faced with a situation that's similar, what if you had something like 2x squared minus 8 equals 0? Well, then you would just isolate the x, wouldn't you? Right? You could do that, because if you add 8 to the other side, now I can divide both sides by 2, because 2 is a constant. I'm not losing solutions if I do that. Right? And the other rule, if we go back to Algebra 2 and pre-calculus, you might remember, you probably remember talking about how if you can point to a single variable, you can isolate it. Right? That's a great rule. If you can point to a variable, you can always reverse order of operations and isolate it. But that's different than what we have in this problem. I can't point to a single variable. There are 2 of them, right? And I can't, they're not like terms, so they can't be combined into one. And so I can't isolate x, I have to factor, right? And it's not a hard factoring process here. What do I do?
Factor out x squared.
Okay, we factor out x squared, leaving us with x squared minus 3, right? And so what are my zeros then?
0 is plus square root of 3.
Good. Okay, so those are all my critical numbers, right?
Plus minus square root of 3.
So it's square root 3, you're right, square root 3. Okay, so now we got our critical numbers. It's just a matter of putting all this stuff in the chart and finding out what these things are, right? So let's do that. Okay, so we had, our domain was everything except positive and negative 1, right? Okay, so we can do that. We can put in a minus 1 and a plus 1, and then we put undefined in the y row, not the y prime row. The function's actually undefined there. And then just do this. Okay. So you can see that you've got vertical asymptotes there, and this is a really good way to show it, because what the vertical asymptotes do is they literally split this thing up into 3 completely separate universes that are just all on their own. So when I want to analyze this function, I've got to analyze it to the left of this vertical asymptote, between the vertical asymptotes, and to the right of this one, all independently. Okay, and this does a good job of kind of visually dividing that up. So then we had our critical numbers at 0, minus root 3, plus root 3, and those were all zeros of the first derivative. Okay, so now what? You take it from there. Yeah, test points. Test points. So what would be some logical test points here?
Negative 3.
Sure. Negative 3 would be to the left of that one. And negative, what's root 3 is about what, 1.86 something?
Yeah,
Negative 2 would work also, sure. What's another?
1.5.
1.5, something like that. So like negative 1.5.
1/2. Or negative 1/2.
Okay. And then I can just do the mirror images of those would be fine. Okay, make sense? And I'm just finding the sign of the first derivative, right? So we've got our first derivative right here. It's already, actually we could make it a little better, couldn't we? What can we do to make that even a little bit better? Yeah, let's factor it as much as we can. Because remember, all we're trying to do is find the sign of the first derivative, and if we can break it into small enough factors, it's really easy to see the signs of those factors then. And then we just do the product rule for signs. You know, if we have an odd number of negatives that are being multiplied and divided, we know the result is odd, and even it's going to be even, right? Or positive. So we can turn that into, how about y prime equals x squared times x squared minus 3 over x squared minus 1 squared. Why is that? I could probably do this, huh? How come those are red? If we're just trying to find the signs of the first derivative, they're always positive, right? So the only term whose sign is in question is this guy right here, isn't it? All these other ones, because the quantities are being squared, we know they're positive. So the sign of the derivative goes as the sign of that factor, doesn't it? And we don't have to see that, I mean, but it just makes it a little easier.
Everything's being squared inside there, so it's just got to be bigger than 3, right?
Right, this, whatever the number is squared, it has to be just bigger than 3, doesn't it? Right, so if we put in a number like negative 3, that's going to be positive, isn't it? Yeah. So we get positive there, 1.5 can be less, right? So that's gonna be negative, 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 right? Okay. Negative, positive. Okay? And how do you show the slant asymptote? I've never found a really good way of doing that on this table. I don't have an idea. I always just write it. I just write it underneath. When you get this slant asymptote like this, it just doesn't seem like there's a really easy way to put that into the table. So I usually just do this. Okay. I guess you could maybe, I don't know, could you put an X right there and I don't know. You could, I suppose. But if you think of something good, tell me. So let's go ahead and try to sketch this thing then. How about? Yeah, for some reason this new version does that. Okay, so there's our there's our table. Let's see if we can get a sketch of this thing. What's this going to look like? I suppose we probably better find some y values, so we can get this thing anchored a little bit. Oh, oops. Forgot what the function was. So if we add a couple y values here, so let's see, if we're plugging in 0, what are we going to get at 0? 0. Okay, so
It's 0 over -1.
yeah, so that'd be 0. Okay, so we get the point 0, 0. How about positive and negative root 3 are going to give the same answer, aren't they? So, actually, no, they're not. That x is cubed at the top. What's root 3 going to give us? If I put in the square root of 3 in for x.
5.2. 3 root 3.
Yeah, on the bottom we're going to get square root of 3 squared is just 3 minus 1. We get 2 on the bottom, don't we? But on the top we're going to get square root of 3 cubed. Square root of 3 times square root of 3 is 3 times square root of 3 is some weird number.
It's 5.19.
So it's roughly good. So we'll just 5.19. That's good enough. We'll just make it a decimal.
Well, divided by.
Divided by 2. Okay. So we'll just approximate it.
2.6.
2.6-ish. Okay. So we had 0, 0. This was about 2.6-ish. And then what if I put in negative root 3? Just flip that to a negative sign in here. And it should just be negative that, shouldn't it? Yeah, just be negative 2.6, right?
Yes, it is.
Okay, so let's see if we can get a little graph of this thing. Okay, where do we start with our graph, do you suppose?
On the outer edges, it's going to be concave down from.
Okay, and in fact, we went through the hassle of finding all these asymptotes, so let's use them, right? We've got vertical asymptotes at positive and negative 1. So let's do those. How about? Oops, off a little bit, isn't it? Check this out, though. Oh, yeah, about that. Okay, so there's those guys, and then we have to get one at y equals x. So let's do that. there are asymptotes. Now, this function, where, oh, I guess we didn't even say what the maxima and minima were. What are they? Where are they? Probably should do that too. We're getting all kinds of stuff here. Is 0 a maximum or a minimum? No, it's not, is it? It's 0. It looks like the function is, it's decreasing the whole time, isn't it? Right? So it's going through this point right here. What's the function going to look like if it's decreasing the whole time? And now we got to use do we have to use this slant asymptote in the middle? So can we cross through the slant asymptote here?
Yeah.
Yeah, no problem. The slant asymptote is for the edges, right? It's for the tails of the function. It has nothing to do with what's going on when x is small, only when it's really big, right?
Negative from both sides of the sharp corner.
Well, doesn't it have to do this? If I'm going to have to use these vertical asymptotes, aren't I going to have to do something probably kind of like this, where it's coming down? One like that. Does that make sense? And we could, if we really wanted to get tricky with this, we could take a second derivative. And if we took a second derivative, I mean, that's a lot of extra work. We weren't asked to do that, so we won't this time. But if we did, we'd find that this is a point of inflection, guaranteed. And so we would have found that it's concave up on this side and concave down on this side. And if you think about that, scratch your head and think about it a little bit, that's the only conceivable way that could look. You know, exactly how curvy it is, you know, we don't have to get that just right. But the basic shape would be that, wouldn't it? Okay, so what about the edges? So what's this guy right here?
Concave down.
So it's going to be increasing to decreasing, right? So it's going to look like that. This goes decreasing to increasing, so it's half face, right? And if this guy is at -√3, so it's about there-ish, -2.6, I gotta go down a little bit. So -1.86-ish, negative, what, 2 point something?
You're still on the mouse thing.
What's that? Oh. So it's -2.6, something like that, so it's down about right here, kind of. And if it's concave down, and it's got to hit both of these asymptotes, anybody want to take a guess what this thing's got to look like? How'd that turn red?
We're on the mouse still when you try to do it.
There we go. So what's that going to look like? I may want to be brave and draw it. What's that got to do? If it's going to be a maximum, it's got to stick to both those asymptotes. Yeah, there it is. Even with the sound effect, that was good. So it's going to go like this. It's going to go kind of up like, it's going to stick to this asymptote. It's going to come up. It's going to max out right there and then go down. That's pretty bad. That should be the maximum, right? But something kind of like that. Okay. We get the same thing up here, aren't we? If this one is a minimum at 1.86-ish, 2.6-ish, it's going to do the same kind of thing. It's going to come down, go like that. How about that? Isn't that cool? So we can just from that table we can see an awful lot of what that graph looks like.
But they really are like three totally separate functions.
And so they're, yeah, you have to treat them like three totally separate functions. Obviously they come from the same equation, but those vertical asymptotes split them completely. So you have to pick, the main thing you gotta remember, and you guys seem to get this right away, is that you have to pick test points, independent test points within each sub-interval, you know, that's carved out by the vertical asymptotes. Okay, so what's this look like if we graph it with a calculator? So if we pull up the calculator here, try the same thing. Okay, so we'll just enter our function. So I get x cubed divided by, remember I gotta have bottom in parentheses, of course. Now you could even write this as fraction. You know how to get to the fraction template in here? If you go, I'll do it this way first and I'll just show you. That's probably the easiest way to do it. If you wanted to though, I'll go down to Y2 here. You can actually go on the 84s if it's upgraded, and if it's not, let me do that for you. If you go alpha F1, you get to this fraction template, and the first one, if I hit 1, look what it does. That's kind of slow. It creates a fraction, so now you can put in rational functions that look just like rational functions. Yeah. But I've already got it in up here. So if we just go, how about if we go zoom 6? That's kind of what we drew, isn't it? Right? Everybody see that? Okay. If I want to find a maximum or a minimum, here's what I can do. I can go second calc, and let's say we want to find the left maximum. I just go down to 4. Do you guys know how to do this? Have you done this before? I just go down to maximum, and then I'm going to pick a left boundary and a right boundary and a guess. So I'm just going to, and I can type in a number. Sometimes it's cumbersome if you want to, if you have to, trace over a long ways. Well, I know that I hit zoom standard, so I'm going by ones. And so if I just count, that's -1, -2, -3. So I could just type in for my left boundary -3. Okay, and there it is, right? For my right boundary, I'll just trace over a little bit. Okay, there it is. Everybody see? For my guess, just go right there, just any place in between. And look what it tells me. Okay. I guess I was off. Negative square root of 3 is not 1.86, it's 1.73. So negative 1.73-ish, negative 2.598, blah, 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 right? And as we said, it was about negative 2.6. So it tells us the coordinates of the peak. I think we can get concavity too. I'm not sure. Let me see. I can't remember. Maybe not. Maybe 9 you can. Oh, can't do it. That's a bummer. That's too bad. That really is too bad. You can't get derivatives though. If I want, you know how to find derivatives. If I want to know what the actual value of the derivative is someplace, I can type the number 6 dy dx, and then I'll just pick a point. Like if I want to go over here, and I want to find the slope at that point right there for some reason. Oh, stop. Right there. I just hit enter, and it tells me dy dx equals. There it is. Okay. That makes sense. That's too bad you can't do concavities. Darn it. The 89s are, I hate to tell you this, but if you're going to, at some point in your career, if you're going to be involved in math or physics or electrical engineering, you probably want to ditch the 84s and get an 89. You don't have to do it right away. I'd wait a couple of years. But
How much more is the 89?
it's a little bit more. It's a little bit more, yeah. They're about, does anybody know? 150, 160, something like that. They're not free, but they're, just so you know, they are actually a computer algebra system. They will do symbolic math, so you can ask them to do, someday I'll take a day and show you what I'll show you what they look like. I want the old ones. You can do things like ask it to take a derivative of some function in terms of x, and it will give you back an answer in terms of x. You can do things, this won't mean anything to you now, but you can have them graph differential equations. I mean, you can find solutions to differential equations with these things. They're really pretty powerful. I mean, they're more than we really need at this level. I like them. That's what we had. Maybe everybody had them. That's what I haven't yet. But these are fine for high school calculus. But at some point, you're probably going to want to make that jump. You can sell these on eBay though and do pretty well.
How much?
So, yeah, you can get almost,
Retail?
close enough that it would have been worth it for you.